Hello and welcome. I hope you're doing well today. This section 3.2, we are looking at the product and quotient rules of differentiation. That is, we want to be able to take the derivative of a product of functions where the derivative exists and the derivative of a quotient of functions where the derivative exists. So here are your formulas in Leibniz notation and Newton notation for the product rule and the quotient rule of differentiation. And we'll notice, first off, that the derivative of a product, for example, is not the product of the derivatives. That is, you don't just find the derivative of f and the derivative of g and then multiply them together. Similarly, for the quotient, we do not find the derivative of f and the derivative of g and just divide those results. Okay, instead we have this formula here. I will show you where this is derived and also a helpful way for us to remember this formula. I've included with this section typed lecture notes that go through proofs for each of the formulas as well as examples included. So before we get into this, I want to make a couple of notes on the product rule and the quotient rule over here. For these rules to be applicable, it must be that f prime of x and g prime of x exist on their domains. That is, on the domains of f prime and g prime. Okay. Now, what does it mean for a derivative to exist? Okay. Well, f prime of x, for instance, exists if and wherever the limit h approaches 0 of f of x plus h minus f of x over h, okay, wherever that limit exists, okay, and exists meaning as a finite number, right? Because if this were to equal infinity or negative infinity, we would say that the derivative does not exist, because we would have a vertical tangent. So this is what it means for that to exist. Now, there's other notation that we have for this. If we use the delta x notation, that is the limit as delta x approaches 0 of delta y over delta x. It's another way of stating this limit of a difference quotient here. Okay, if this limit, okay, is equal to f prime of x, in other words, if this exists. Okay. Now, recall that differentiability, which we're saying this function has, and similarly for g prime of x to exist, it has differentiability within its domain. Okay. Diffability implies what other feature of the underlying function? We said that if a function is differentiable at a particular value, then it also must have what other characteristic at that value? And that characteristic was continuity. Okay? When a function is differentiable at a value, then it must be continuous at that value. If a function is differentiable on an interval, then it must be continuous for every value within that interval. Now, what is continuity again? Continuity is that the limit of a function is equal to the function evaluated at the point where we're trying to take that limit to. Okay, but also we have the geometric interpretation of continuity. Take a look at that. For a function to be continuous at a particular value, let's say like here, for instance, this function that I've just drawn here is continuous. Okay, we'll call this at a right here. All right, and then the output y is f of a. Well, if we moved out to a point, let's say a plus h, where h is greater than 0 right now, okay, then we would have an output of what? F of a plus h right there. Okay. Now, the difference between a and a plus h, the difference between these is h, or we can call that delta x, right? The difference in the x values, okay, as I've used in this notation right here and demonstrated here. And the difference between these y values, okay, the difference between these y values right here, from here to here, all right, that distance, okay, we can call that delta y. It's equal to f of a plus h minus f of a, okay, for a particular value of a. More generally, f of x plus h minus f of x for every value x, for example, within the domain of interest. So this is our delta y. And I could also call that a delta f, because we'll be using this notation in the proof a little bit later. Notice, because the function is continuous at a, right, we can see f is continuous at x is equal to a. Okay? Then what that means, one thing that means here geometrically, is that delta y shrinks down to 0 as delta x shrinks to 0. Can you see that that's happening from the graph? As we move a plus h towards a, the resulting output f of a plus h, notice, moves down towards the value f of a. Because the function is continuous at a, this is guaranteed. Right? If delta x shrinks to 0, if these two values get really close, by continuity alone, the difference in y values would also approach 0. Where did we see that relationship before in the difference quotient? Right, that both of these quantities are going to 0. So in other words, the ratio delta y over delta x, okay, we have the numerator going to 0, the denominator going to 0. Okay, that's happening as we are allowing delta x to approach 0. Delta y is approaching 0, right? And this was the indeterminate form that we get every time that we try to run the limit of that difference quotient. Okay, so delta x is the same as h. Delta y is the same as, let's say, f of x plus h, or in this case, f of a plus h. Okay, minus f of a over h, right? This is always going to 0 over 0 by continuity of the function, which was a requirement to have continuity in order to say that the derivative itself actually existed. So for a function to be differentiable, it must have continuity. And if the function is continuous at a particular value, then it means that as we push delta x to 0, the corresponding delta y must go to 0 as well by continuity. Okay, now back to our example over here. Okay. So in order to show that the derivative of a product is in fact not the product of derivatives, okay, all we need is a single counterexample. That is, let's choose two functions that we know are differentiable and then take their derivatives. Multiply the derivatives of those two functions and see what would have been the derivative if we had done the multiplication first. And here's an example right here. Let's say f of x is x cubed and g of x is x squared. Okay, and our goal here is let's find the derivative of the product of f of x and g of x. Well, one way that we can do that is to multiply f of x and g of x together. Okay? That's what I'm doing right down here. Take the derivative of the product of f and g. Well, f of x times g of x algebraically would be x to the fifth. That is, if we did the algebra first and then did the calculus, f of x times g of x would be x to the fifth, and the derivative of x to the fifth is 5x to the fourth. That would be true, and that would be correct. The derivative of this product, x cubed and x squared, is 5x to the fourth. That is the correct answer that we should get. Now, what if we tried to do it by taking the derivative of f, which is 3x squared, and the derivative of g, which is 2x, and then multiplied those two derivatives together? Do we get the same answer? And we can see here, no, we don't. The product of the derivatives is 6x cubed, not the same as doing the product first and then calculating the derivative. These two answers don't match. So when we need to, in general then, when we need to find the derivative of a product, we do not multiply their derivatives together. The same is going to be true for the quotient. For the same two functions, x cubed and x squared, it can easily be shown, I show it down here, that what you want to do is, in order to find that derivative, okay, you can algebraically simplify the quotient first, if possible, and if it's not too expensive to do so, algebraically expensive that is, okay, you can find the quotient algebraically and then take the derivative of the result, and that would give you a correct answer. So for instance, f of x divided by g of x, x cubed divided by x squared, that would just equal x. And then the derivative of x, well, that's just 1. And that would be the correct value of the derivative of this quotient, x cubed over x squared. But if we tried to take f prime of x, which was 3x squared, and divided it by g prime of x, which is 2x, we don't get the exact same answer. Instead of getting the answer 1, we get the answer 3/2 x, which it's only true that 3/2 x can be made to equal 1 at a specific value of x, in this case if x was 2/3, but for any other value of x, in this case within the domain, all real numbers, any other value of x other than 2/3, this answer would not match that answer over there. All right? So again, this demonstrates that the correct way to take the derivative of a quotient, okay, is not to take the independent derivatives and divide them by each other. Okay, so instead, we have one option here. If we can simplify algebraically first, either the quotient or the product, algebraically simplify it first, and then take the derivative, we know we're going to get the correct answer. It's an order of operations thing, working from the inside out. But what if we are unable to simplify the result algebraically before taking the derivative? Okay. In those cases, then, what would we do in order to find the derivative of a product, okay, for instance, or the derivative of a quotient? Okay. Let's take a look at an example like what I mean. When does the algebra not help anymore? Okay. Consider this example. Let's take f of x is equal to x times e to the x. Okay? And now let's say we wanted to find f prime of x. How can we do it? We can't simplify this any further than this algebraically, notice. Right. If we had something like x squared plus 1 times 2x cubed minus 5, something like that, okay, we have an option here that we can actually FOIL this, we can expand this, and we'll end up with a set of power functions, right? We'd have a 2x to the 5th minus 5x squared, then we get plus 2x cubed and minus 5. And then we can take the derivative term by term here without having to use any kind of special rule for the product. Okay, that would be possible. But because of this combination we have here, power function times exponential, there's really nothing we can do to simplify this beyond this point before we take that derivative. So the question is, how do we find this derivative? Okay, so now let's step away from this example for a moment and take a look at, in general, how we would define the derivative, y prime, if y is equal to a product f of x times g of x. Okay, so we're only going to be looking at where the derivative actually exists. Okay, now f prime of x and g prime of x, let's say that they exist. Each of those exist in order for this to work. Another thing is that, well, let's take a look at the limit definition. Right, one way we could write it is the limit as h goes to 0 of the product fg at x plus h minus the product fg at x over h, for example. Okay, now algebraically what this means when we have a product with an input, it's the same as saying that we can evaluate each of the functions at that input. Okay, so this is the limit as h goes to 0 of f of x plus h times g of x plus h minus f of x times g of x, and all that is over h. Okay. Now let's take a little closer look at this f of x plus h. What does that mean? For instance, does something like f of x plus h, does that necessarily equal something like f of x plus f of h? Okay, can we distribute the function f? And the answer to that is a resounding no. It depends on the function itself. If you need an example to demonstrate that that's so, okay, consider an example like f of x equals, how about the square root of x? Okay, f of x equals the square root of x. And notice that then f of x plus h for the square root of x function would be the square root of x plus h. But f of x plus f of h would show up as square root of x plus the square root of h. and these two sides are not equal to each other, right? So for many functions we can define, it is not true that we can distribute f. That's not true. We can't do that. So we can't write this as an f of x plus f of h. Well, let's use a little bit of geometry here for a moment then. Okay? How about instead, let's consider... Okay, let's consider a function like f of x is equal to x squared. And again, note that f of x plus h is not equal to f of x plus f of h for this example, right? If for f of x equals x squared, we would have f of x plus h is x plus h squared, okay? But f of x is x squared, and f of h would be h squared, and these are not equal to each other, right? The way to expand this left-hand side is, of course, by foiling, and you would get that extra term, that 2xh term. So these two sides are not equivalent to each other. So again, you can't distribute f. But let's take a look at f of x equals x squared geometrically for a moment. Okay, just a sketch, of course. All right, so let's choose a particular place to look at this. Okay, and then we have the output. Okay, here's our fixed point, a, f of a. And then if we move away from there to a location a plus h or a plus delta x, okay, then we get the output there would be f of a plus h, or f of a plus delta x. Now, the difference between these x values is h, of course, right? When the difference between these x values is h. The difference between these y values, though, we can call that delta y, or we can call it delta f, for example, right, as we did previously. And we can see that it's not necessarily true that delta y is equal to delta x. And we know that from our epsilon delta proofs. Consider that, you know, if this difference here, if we had called this delta in an epsilon delta proof, this distance here would be called epsilon. And recall that it was not true that epsilon and delta were always equal to each other. All right, for different values of epsilon, you can get different values of delta. And in general, for a distance epsilon that is chosen, okay, in general, there would be a value of delta associated with that particular epsilon, but they are not equivalent to each other. Okay, so when we are looking at f of x plus h, for example, or in this case f of a plus h, we can say that f of a plus h, clean that up a bit, f of a plus h can be said to be equal to f of a plus some delta y or delta f quantity, where that delta f is this distance here, right? The difference between these y values. So that would be okay to do. And delta f is the same as delta y, by the way. So f of a plus a delta y, for example. And this would be true at any point whereby the derivative exists, so this is true also for f of x. We can say that f of x plus h is equal to f of x plus delta f, or f of x plus delta y. Okay? Where h is the same, by the way, h is the same as delta x. So this is the same as saying f of a plus delta x. And this is the same as saying f of x plus delta x. Okay, so now back to this statement here. So we have the limit as h goes to 0 of, and let's start expanding this, f of x plus h is the same as f of x plus a delta f. Similarly, g of x plus h is the same as g of x plus a delta g. Not g of h, right? Not g of h, but instead a change in the output as a result of changing the input. Okay, not g of h. Okay, and then we subtract from that the f of x, g of x that we have right here, and all of that is now being divided by h, or we can call that delta x, either h or delta x. Okay, now let's do some algebraic simplification. So we can expand these terms in the numerator. We're going to have an f of x times g of x right here, and then we're going to subtract an f of x, g of x out here. So those are going to cancel. And then we're also going to get an f of x times delta g from here, and then we're going to get a delta f times g of x from here, and then finally we're going to get a term that is the product of the deltas, a delta f delta g, and that's over h. Okay? And this is exactly the same as saying this. The limit as delta x goes to 0 of the same expression. F of x delta g plus delta f g of x plus delta f delta g. And now what I'm going to do is, since delta x or h is a common denominator, I'm going to put that as the denominator of each one of these terms. So we have a delta x for that term, a delta x for this term, and a delta x for this term. And we are running the limit as delta x approaches 0 of these three terms then. Okay. Now take a look closely inside of each of these terms. This first term we have delta g over delta x. But what is delta g over delta x? Well, we already said that g prime of x existed. G prime of x exists. If g prime of x exists, that means that g prime of x is equal to the limit as delta x approaches 0 of delta g over delta x. And that's what we're looking at here. All right? Now, delta x going to 0 doesn't affect x itself. Right? Just as when h goes to 0, it doesn't change what a is equal to. Right? So we think of x as a fixed value. That's not moving. Okay? But delta g over delta x, as delta x goes to 0, this is going to equal the derivative. So this first term, when we run this limit, we get f of x times g prime of x from that first term. Similar argument here on the second term. We have a delta f over delta x. And as delta x goes to 0, what do we get? Again, now we have f prime of x exists. If f prime of x exists, then f prime of x is equal to the limit as delta x approaches 0 of delta f over delta x. And that's exactly what we're looking at here, right? So this is going to be plus f prime of x times g of x. Now on this third term, we have only one instance of delta x in the denominator, but a delta f and a delta g in the numerator. Okay, so we're not applying this delta x to both of these. We have to pick one. So for instance, if I put it with the delta f right here, then the limit as delta x goes to 0 of this ratio, delta f over delta x, that would be f prime of x, but we still have that that's multiplied by delta g. Or we could have instead applied the delta x, kept it in a ratio with the delta g if we wanted to, and then that would have left us with a g prime of x, but then we would have had a delta f without a denominator of delta x with it. Okay? In either case, by continuity, what's going to happen? We have a delta g in one case and a delta f in the other case. Okay? So the answer is that by continuity of f and g, okay, we have that as delta x goes to 0, it must be that delta f goes to 0 and delta g goes to 0. As stated earlier, we know these functions are continuous because they're differentiable. So although one of these two numerators is going to get absorbed into a derivative, we're going to be left with the other one that is still going to go to 0. And if it's hard to see how that's the case, consider this example. Consider if I wrote a quantity like, and this is a very, this is not the example that we're talking about here, but say I wrote an example like x minus 1 squared over x minus 1. And what happens as we take the limit of this as x goes to 1? We have a removable discontinuity here, right? This is a 0 over 0 situation. We do have that, right? X minus 1 times x minus 1 over x minus 1. Now we have the option of canceling the denominator, x minus 1, with either of these two factors of the numerator. But we can't cancel it with both. So whichever one we choose to cancel it with, we're still left with another one that is approaching 0. So in the end, no matter which way we cancel this denominator, we still end up with 0. The only way that we could have canceled both is if we had x minus 1 squared in the denominator. We had to have two denominator factors going to 0 that were each canceling the numerator's factors. Right? That's the only way that we really could have gotten both of them to cancel, which would have given us we would have removed two discontinuities and could have given us a product of derivatives instead. Okay? So notice instead in this case, no matter how we look at this expression here, this term right here, it is going to 0, right? No matter what, right? No matter how we look at this term, it is strictly going to 0. And so we are left then with a conclusion. Okay? We were trying to find the derivative, okay, the derivative of a product here. By the definition, fg prime is equal to this, and that leads us to this result right here. So therefore we have the product of f and g, the derivative of a product, would give us f times g prime, okay, plus f prime times g. And that's our formula for the product rule. Okay, so I go through this product rule here as well. Some slightly different notation, but again, I just wanted to run through it with you here so that you can really understand, okay, how we are applying the algebra and the notion of continuity as well, okay, in order to derive the product rule. Now we're going to take a look at some examples with the product rule. Okay, I want you to take a look at the quotient rule. The proof for the quotient rule is quite similar. Here we have, for instance, a quotient of functions evaluated at x plus h. So that is f of x plus h over g of x plus h, and then we have an f of x over g of x. And remember that f of x plus h is the same as f of x plus delta f, not f of x plus f of h, right? It's f of x plus delta f, and then we have g of x plus delta g. So we combine these with a common denominator, right? So we multiply this first one by g of x, we multiply the second one by g of x plus delta g, then we distribute, and then we combine like terms, and when we do that, we are left with this expression here, okay? This expression here. And now we push h to 0, or delta x goes to 0, and that causes delta f to go to 0 and delta g to go to 0. Now when we have delta f is going to 0 while h is going to 0, that is, we're getting 0 over 0, that gives us the derivative, f prime, because it exists. And similarly, delta g over h, that goes to 0 over 0, removable discontinuity, that ends up going to the derivative g prime. But when we have g plus delta g, here, since h is going to 0, again by continuity of g, delta g goes to 0. But it's not being divided by anything. It's not being divided by another quantity going to 0. It's just going to 0. So we're left with a g squared in the denominator. So we end up with our quotient rule defined this way. The g, which is the denominator function, times f prime, the derivative of the numerator, minus f, the numerator, times the derivative of the denominator over the denominator squared. And a way that we have to remember that, one way I have for you to remember that, is to sort of remember it this kind of sing-songy way. Okay, if we call the denominator function the low function and the numerator function the high function, we can remember low d high minus high d low over low low. Or low d high d low, don't forget to square below. Two ways that we can remember the quotient rule. That is, you take the lower function times the derivative of the higher function, okay, minus the higher function times the derivative of the lower function, and then square the denominator function. Okay, you don't take, in the denominator, the new denominator is not a derivative, right? The denominator is just the square of the original denominator function. And that's how we do the quotient rule. Okay, low d high minus high d low over low low, or low d high minus high d low, don't forget to square below. So remember the quotient rule that way. Okay, now let's try some examples. We have several here. You also have a worksheet, plenty of examples on your worksheet here. Okay, let's start with the one that I wrote down a little bit earlier. How do we find the derivative of this product? Well, we now have a product rule. Okay, use the product rule for differentiation. Okay, and now let's apply it to this. So we have, all right, so we have two functions here. Yeah, we have the first function is y equals x. The second function is a y equals e to the x, for example. Okay, so this is a product of functions. So f prime of x, okay, our product rule You can commute these terms. It doesn't matter. It's that each of them are mixed terms. You have the product where you keep one of the functions the same and you take the derivative of the other function. And it doesn't matter which order you do that in, because we're adding these results together. Contrast that with the quotient rule. In the quotient rule, it does matter which order we do this. This is important to notice because we have subtraction. It must be, for the quotient rule, it must be low d high as the first term, then minus high d low. You can't switch those around. Okay, so that's important to note. But with the product rule, the order doesn't really matter. It's that you're taking one of the functions times the derivative of the other, okay, and then you switch them around. So let's do that here. So I'll leave the first function alone, that is x, I'll just leave that alone, okay? And then really, I'll write this out notationally. We're multiplying by the derivative of e to the x, and I'm using Leibniz notation there, Newton's notation on the left. So we have, leave this alone, derivative of that, plus, now we take the derivative of the first, that's the derivative with respect to x of x, and then we multiply that by the second function left alone. Okay, now let's take our derivatives. The derivative of e to the x is e to the x. And the derivative of x, well, that's 1. And then we have an e to the x again. Okay, now here's our answer. Okay, we've shown with the product rule, we've shown all the, the correct results in the correct combination. But how about simplifying? How would the answer look in the back of the book, for instance, or in a solutions manual? Well, we're probably going to see that e to the x is factored out from the two terms, and what we're left with is an x plus 1. So e to the x times x plus 1. Most likely way that we would see this derivative of this product written in a solution manual, for example. So now we know how to take the derivative of a product. We can start applying, we can start pushing it further to include things that we have been doing with derivatives. We can take, for instance, higher derivatives. We can now find out what is the second derivative and the third derivative of this example, if we want to. We can also answer application questions about, like, for instance, the tangent line or the normal line. What would be the equation of the tangent line to this function at a given point? Like, for instance, when x is equal to 0, which it turns out f of 0 is equal to 0. So we can say, what's the equation of the tangent line to this function at the point 0, 0? We can ask the question, what's the equation of the normal line to this function at the point 0, 0 as well? Right? So we can do all the things we have been doing so far with derivatives now with products of functions because we have the product rule. But that does not mean that we always need to use the product rule, however. Okay, let's take a look at an example where you have an option. Okay, find y prime in two ways. A, we'll do so by doing algebra first, that is to expand and then differentiate. Okay, and B would be by use of the product rule. Okay, and for y, let's take y is equal to x cubed plus 1 quantity squared. Okay, so two ways to find y prime. A, algebra first, that is expand. So y prime is equal to x cubed plus 1 times x cubed plus 1. Sorry, that's not y prime, right? That would be y. Okay, here we go. Y is equal to x cubed plus 1 times x cubed plus 1, which when expanded is x to the 6th plus 2x cubed plus 1. Okay, so we've expanded y. Now we can find y prime by taking the derivative, all right, of this expanded result. And so we can distribute the differential operator, and then we can use the general power rule. So term by term, 6x to the 5th, the general power rule, plus 6x squared, and then plus 0, because the derivative of a constant is equal to 0. Okay, so there's an answer. Okay? And yeah, another way we could write it is 6x squared times x cubed plus 1. Okay, so we have y prime is equal to this, or y prime is equal to that. Okay, And here we distributed the differential operator. That is the sum rule. We can distribute the differential operator. And we did the general power rule, okay, in order to find the individual derivatives. So that's A. So that's one approach we can take for an example like this. B, use the product rule instead. Let's see how that would work. Well, we have y is equal to x cubed plus 1 squared, which we should write as a product. We have not yet dealt with compositions of functions, which this is written now as a composition, where we have x cubed plus 1 inside of the x squared function. That requires another rule for us to look at called the chain rule, and we'll do that later. But let's use the product rule. Let's write this as a product, okay? And then by the product rule, what we do is we leave one of the functions alone, x cubed plus 1, and multiply by the derivative of the other function. Okay, so we're going to take the derivative of the other x cubed plus 1, then plus, now we're going to take the derivative of the first function and multiply that by the second function unchanged. Now the derivative of x cubed plus 1 is 3x squared plus 0. All right, so we have x cubed plus 1 times 3x squared plus 0, or just 3x squared. And of course that gets repeated here for this example. We happen to repeat that. 3x squared plus 0 times x cubed plus 1. And this shows, in this step, this shows we have done the product rule. Now, is the answer going to be the same as the answer we got up here? Either one of these two answers, which are equivalent? Okay, let's see. So y prime is equal to x cubed plus 1 times 3x squared plus 3x squared times x cubed plus 1. We can factor out x cubed plus 1, and that's going to leave us with 3x squared plus 3x squared. In other words, we can write this as 6x squared times x cubed plus 1. And that does match exactly with one of our answers up here, 6x squared times x cubed plus 1. All right. Now let's take the product rule even a little bit further. Okay. Find y prime if y is equal to, let's do x cubed plus 1 to the third power now. Okay, and use the product rule. We already know we can do this by expansion. Okay, we saw that, and then we can go term by term. But let's try to see how does the product rule work here. Okay, well, notice that if we write this as a product now, we write it as a product of 3 functions, right? X cubed plus 1, x cubed plus 1, x cubed plus 1. So we have here something like y is equal to f of x times g of x times h of x. And in that case, how does the product rule work? Okay, how's the product rule going to work? Well, we should group together 2 of these as one, okay, as one function. Okay, so if we group together f and g, for instance, f times g, okay, then we can deal with the product rule in this way. We can leave the product f of x, g of x. Let's write it as f times g. We can leave that product alone times the derivative of the remaining function, and then plus, and now we're going to have to take the derivative of this product, fg, and then we leave h alone. But we're not done, because now we have a derivative of a product within our product rule. So we have to continue. So y prime is now equal to, okay, we'll leave it in parentheses, fg and then h prime, but then fg prime itself is a product rule. So that's fg prime plus f prime g, and then that's times h. So we can do a product rule within a product rule, okay, in order to deal with when we have a product of 3 functions. And you might rightfully assume that if we had a product of 4 functions, we would need to do product rule within product rule within product rule. Okay, for each product, 1 product, 2 products, for each time we are multiplying functions, we would have to apply the product rule for each one of those multiplications. What we do not do is we do not take the derivative times the derivative times the derivative. Right? That is not going to work. we need to follow the product rule itself. All right, so let's see. So I have y is equal to, okay, let's say we leave x cubed plus 1 times x cubed plus 1 alone, or we could call that x cubed plus 1 squared, and then multiply that by the derivative of x cubed plus 1, which is 3x squared. Okay? Then, after that, we're going to want to add, okay, the derivative of the product. Okay, I'll put that down here. Okay. So we're going to want to add the derivative of the product x cubed plus 1, x cubed plus 1. Okay, times the remaining function unchanged. All right, that would be y prime. So this is y prime is equal to, now let's clean up this first term. We have 3x squared times x cubed plus 1 quantity squared from that. Then we get a plus, and then we have, let's see, I'm going to leave this x cubed plus 1 right here. Okay, I'm going to push that to the front right there. And then we need to take the derivative of this product. But I think we already found the derivative of that product, right? Right up here. The derivative of the product x cubed plus 1 times x cubed plus 1 we had simplified as this. 6x squared times x cubed plus 1. Okay? So let's make a note. This was done previously. See above. Okay? Just above here in this exercise. All right, so here we go. So otherwise, if we hadn't done this part previously, we would need to find, we need to do this product rule right now as well. But here, okay, we have completed 2 product rules by this step. Okay, that is, this was a product rule right here. Okay, and then this was a product rule right here. And we could clean this up, all right? We could leave the answer in this form for grading purposes so that I can see all the things you did. Of course, this part right here, the work for that was done up here. Okay, so I need to be able to see all those steps in your work. But if you're checking your answer in a solution key, you're probably going to see a cleaned up answer. Or if we're going to then apply this to something else, like if we wanted to then set this value, this expression equal to some quantity, let's say geometrically we wanted this to be equal to the slope of some line that we have predetermined, then we would want to be able to solve an equation involving all these expressions. Okay, and it might be most convenient for us to simplify this as much as possible before trying to solve such an equation. So there could be reasons why we'd want to simplify this. Okay, we have an x cubed plus 1 squared right here. And then we have an x cubed plus 1 times an x cubed plus 1 here. So I could factor out an x cubed plus 1 squared. See that? X cubed plus 1 squared. We also have here, let's see, a 3x squared. Let's use blue. Here we go. 3x squared right here and a 6x squared here. So we could take 3x squared out of both of these terms. So 3x squared and x cubed plus 1 squared. 3x squared from here, okay, and x cubed plus 1 squared. This is going to leave us with a 2, just a constant 2, okay? But in order to distribute this to get back this original result, right, we'd need to have, let's see, a 1 from here plus 2 from here. And so y prime is equal to 3 times 3x squared gives us 9x squared times x cubed plus 1 squared. Even when we're using, as powerful as calculus is, right? Even when we're using a lot of the calculus, we cannot escape the algebra itself, right? The algebra can trip us up. All right, so one place you would be using your algebra here could be in expansion. Another place could be in contraction, in simplification. You might be simplifying for a variety of reasons. One of them could be to try to show that your answer that you got is equivalent to an answer that you see in a solution key. and other reasons could be involved in applications like tangent lines and interpretations of instantaneous rates of change, for example. Okay, so now let's take a look at a quotient rule exercise. So we have some in here. You can see that B right here, this is a quotient rule. We have a quotient of two functions. The way to remember the quotient rule, low d high minus high d low. Don't forget to square below, or low d high minus high d low over low low. Okay, so we could do it on that one. But I want to jump ahead to this one because I have an extra feature here that I want to discuss, which is we are given a function here, right, with no numerical values. But what are the variables? When we take the derivative of this function h of r, right, what is the variable with which we are taking the derivative with respect to? The input variable is not x. I want to note that in the notation of the function itself, we are told that the output variable is h and the input variable is r. So when we are taking the derivative for this function right here, we assume that we are taking the derivative with respect to r because that is the input variable as stated in the notation of the function itself. That means that a and b, and certainly e, which is already a constant, but a and b are considered to be constants here. They're parameter values. And they are not varying with respect to this, okay, with respect to the derivative we're going to be taking. Okay? So let's take the derivative of this. Let's find h prime, and we would be doing h prime with respect to r, and we're going to require the quotient rule in order to do so. All right, so find h prime. Okay, Newton's notation suggests that we are taking a derivative with respect to the single variable in the input. Okay, if we were using Leibniz notation, okay, we'd be saying dh over dr. We would be specifically stating which variable it is. Here we can say h prime of r as well. But even if it just says h prime, okay, we take a look at the notation for the function to determine, well, which variable is it that we're taking the derivative with respect to. Okay. All right, so we had the function a times e to the r over b plus e to the r. Okay. So notice by the notation, r is the variable, a, b, and of course e, those are taken to be constant. Okay, constant is the natural growth constant, approximately 2.718. Okay, so we are finding h prime of r in Newton notation, which is the same as dh over dr in Leibniz notation. We've applied the differential operator with respect to r to the function h. Okay, and this requires the quotient rule to do, the quotient rule. Okay, that is low d high minus high d low over low low. All right. Okay, and in this case, the high function, okay, right, the high function, if you will, is equal to the output a e to the r, and the low function is b plus e to the r. Okay. So let's apply the quotient rule. So we have the low function b plus e to the r times the derivative of the high function. So I'll write a e to the r prime, okay, minus high, which is a e to the r, d low, so that would be b plus e to the r prime over low low, so the low function squared. Okay, so let's find our derivatives, our independent derivatives here. So we have b plus e to the r, and then what is the derivative with respect to r of a e to the r? Right, the derivative with respect to r of a e to the r. Well, a is a constant, so we can factor that out, okay, and then take the derivative of e to the r with respect to r, which is just e to the r. So we get a e to the r. Okay, so this is a e to the r. Minus, we have a e to the r. What is the derivative of b plus e to the r. That is with respect to r. d over dr, b plus e to the r. That's going to be, since b is a constant, the derivative of b would be 0. And then we take the derivative of e to the r, which is just e to the r. Okay, so this is just e to the r. Okay, and then we have this over b plus e to the r quantity squared. So this is an answer that expresses we have used the quotient rule. Right? We see all the individual components of the quotient rule. Now, for simplification purposes, how can we simplify this? Well, the numerator, let's look for some common factors here. We have ae to the r and another ae to the r over here. So I'll take out ae to the r, and that leaves behind in the first term, let's see, b plus e to the r, and then minus, from the second term, we were left with an e to the r. And then the denominator is b plus e to the r, quantity squared. Now we can cancel these e to the r's right here, okay, and clean up the numerator. Let's write it in alphabetical order. A, b, e to the r. And the denominator is b plus e to the r quantity squared. And so there's our derivative by use of the quotient rule. Now let's take a look at another exercise from the worksheet. I'd like to take a look at J. Something I find interesting about J is that we have a quotient. That's the bigger picture here, is we have a quotient of two functions, but then if you look in the denominator itself is a product. So that is, we are going to need to use a product rule within the quotient rule. When we take the derivative of the denominator, the d low, at that point we're going to need to use a product rule. So we need a product rule inside of a quotient rule to do letter J. Let's try that. So for letter J, it's find v prime of t, where v of t is equal to 4 plus t over t e to the t. So we have the high function is 4 plus t, the low function is t e to the t. Okay, and so we start with a quotient rule. Okay, start with a quotient rule. Low d high minus high d low. Don't forget the square below. Okay, so starting with low, that's t e to the t. D high, okay, so we're going to need 4 plus t prime, right? The derivative of that. Minus high, which is 4 plus t, times the derivative of the denominator. So t e to the t prime, okay? And then the denominator will be squared. Okay, so let's compute some derivatives here. All right, we have 4 plus t prime. Okay, let me sort of separate this. Okay, 4 plus t prime, but we're taking the derivative with respect to the variable t. Right? So we have derivative with respect to t of 4 plus t. Well, that's just going to equal 0 plus 1. In other words, just equals 1. Right? Now, when we take the derivative with respect to t of t e to the t, right? That's where we're going to need to use a product rule. Right? So we have the first function times the derivative of the second function plus the derivative of the first times the second. Okay, and we did this one earlier. We did x e to the x as the first example with the product rule, so we already saw what this is going to give us. But again, this is t e to the t plus 1 e to the t. In other words, it is e to the t times t plus 1 by the product rule. So that's a product rule right there. All right, now we needed to do that product rule in order to complete our quotient rule. So this is t e to the t times 1 minus the quantity 4 plus t times, we simplified our derivative here, e to the t times t plus 1. And all of that over this quantity. Okay, I'm going to leave this denominator then in this form, because we might be able to cancel some factors here. We'll see. All right, let's clean up the numerator now. But now this step right here demonstrates the quotient rule. So we've completed the quotient rule now. Okay, and in that quotient rule, we had to do a product rule, of course. Okay, now let's clean up the numerator a bit. We can factor out from the numerator. It looks like we have a t and an e to the t here. We have e to the t over here, so we can factor out e to the t from both of those. Then in the first term, that leaves us with t, and then minus, and now we have the quantity 4 plus t, and we have the quantity t plus 1. So 4 plus t, t plus 1. And the denominator we have, well, this can be written as t squared times e to the 2t. E to the 2t is the same as e to the t times e to the t. This is, sorry, v prime of t. I need to be correct on my notation here. We have been finding v prime of t this whole time. Right, this was v of t up here. Okay, so v prime of t, cleaned up further, now we can cancel one of these e to the t's here with one of these down here. Okay, so the denominator now is t squared e to the t. And the numerator, let's see what we get if we FOIL this out. It looks like we get 4t, okay, and then we're going to get a plus 4 plus t squared plus t, okay. And now looks like when we distribute this minus sign, it looks like we'll be able to cancel this t with this t out here. Okay. So v prime of t now is equal to negative, I'm going to put these in standard form, t squared plus 4t plus 4 over t squared times e to the t. Okay, and we can even clean it up a little bit further because this factors really nicely here in the numerator. It factors as a perfect square of a binomial, so it's the quantity t plus 2 squared. That negative is in front, and then t squared e to the t for the denominator. And this answer here is likely to be the most simplified form of the answer that you would find like in an answer key. Okay, and also useful if we wanted to apply this derivative in many other situations, depending. A lot of the times when we're applying the derivative in this course, we'll be setting our derivatives equal to 0, for example, and solving the resulting equation. And in those cases, we're going to need to apply algebraic technique in order to solve the equation. Things like factoring, combining like terms, common denominators, those are all going to be important algebraic techniques to be able to apply in order to further use these derivatives for a lot of cases of things that we're going to do. All right, certainly not if we were just going to plug a value in. If we wanted to find out what is v prime of 3, for instance, well, we could plug 3 into our formula that we have right here and evaluate what that equals to. Okay, so here's our cleaned up answer. What am I looking for in the grading? I'm looking for your notation. All right, I made the correction a moment ago. They need to be calling this v prime and not v. Right, v of t was this function here. This is the derivative. And I'm checking to see, did you use the quotient rule? I need to see all your, all your terms written out. This is what I'm looking for. That I'm looking for a low d high minus high d low over low low combination for the particular low and high functions that we were given. All right. And in this case, that quotient rule required the use of an additional product rule. So I would also need to see either within the quotient rule itself or off to the side where you're also doing that product rule. So I would be checking for both of those things. Okay? And that's where the credit would come from. If all you're being asked to do is find the derivative, that's what I'm looking for right there. I'm not looking for the simplification that you can get, okay, in the end right down here, necessarily, unless it's in the actual instructions to the exercise. But again, I've said more than once, there are reasons why you would want to do the simplification. If you want to check to see if your answer matches the answer in the back of a textbook or in a solutions manual, you might need to do the simplification in order to see if your answer matches their answer. And if you wanted to use this derivative in an application, you might need to do the simplification in order to actually do the application. Okay. All right, let's take a look at another type of an example here from the worksheet. This one right here. Question number 2. Now suppose that we're given not the rules of the functions, not what does f of x equal, what does g of x equal, but let's say we're given actually evaluations. We're given an f of 4, a g of 4, also f prime of 4, and g prime of 4. And then we're told different combinations of how f and g can be combined together in other functions, right? So without the symbolic rules of the functions. Let's try D. We are given that h of x is the combination g of x over f of x plus g of x, where we don't know what g of x and f of x are, right? But we're asked to find h prime of 4. H prime of 4. Find the derivative of this and evaluate it at 4. Okay? Which in general, I would remind you, as I noted in a previous section, when you're finding now the derivative at a value, you find the derivative of the function first, in general, with respect to x, then plug the value in. Because if you plug the value 4 into the function first, it reduces to a number, and then if you took the derivative of that result, you would always just get 0. Because the derivative of a constant is always 0. So anytime that we are doing something like an h prime of 4, we should find h prime of x first, and then plug 4 into the result. That's the way we do it. Okay, so that we don't get 0 every time. Okay, let's try 2D then. Okay. Find h prime of 4. Okay. Big picture here, we're looking at a quotient. Okay, h of x is a quotient. So we'll find h prime of x by use of the quotient rule. Okay. So h of x is a quotient. So low d high minus high d low. Don't forget the square below. Okay, so we have, starting with the low, which is f of x plus g of x, times d high, so that's g prime of x, minus the high, which is g of x, d low, we're taking the derivative of f of x plus g of x. By the sum rule, that means we can take f prime of x plus g prime of x. And then the denominator is f of x plus g of x quantity squared. Right, so now h prime of 4, we can evaluate. Okay, we're plugging 4 in. So we have f of 4 plus g of 4 times g prime of 4 minus g of 4 times f prime of 4 plus g prime of 4, all of that over the quantity f of 4 plus g of 4, that whole quantity squared. And now let's start plugging in what we know, right? All these quantities we know. F of 4 is given to us is equal to 2, all right? F of 4 is equal to 2, g of 4 is equal to 5. So this is 2 plus 5. G prime of 4 is negative 3, and then minus, and then g of 4, again, that's 5. F prime of 4, that's 6, plus g prime of 4, which is negative 3. Okay, so we'll write 6 minus 3. F of 4 plus g of 4, that would be 2 plus 5, and then that quantity is squared, right? So 2 plus 5 quantity squared. And now let's evaluate this. So that's 7 times negative 3 is negative 21. We have negative 5 times 3. Okay, so that's negative 15, right? And then 7 squared on the bottom, that's 49. So this is going to give us negative 36 over 49. That's it. Okay, so you've seen a tangent line and normal lines to a curve at a point. Okay, so you can try this exercise on your own. Okay, given a function at a point. Let's take a look at this one. Find equations of the tangent lines to the curve, y equals x minus 1 over x plus 1, that are parallel to the line x minus 2y is equal to 2. How do we do that? In order to find equations of tangent lines, we need to compute the derivative. Right? So we need the derivative of this function, and since this function is a quotient, we're going to need to apply the quotient rule to find that derivative. Now that's going to give us the derivative as a function, that is y prime of x. We need to actually find then the points on the curve such that that derivative would be parallel to the line x minus 2y is equal to 2. Now, in order for lines to be parallel, the tangent line and this line, in order for lines to be parallel, they have to have the same slope. So we need the slope of the line that we're given, and we need that slope to be what the derivative of our function is equal to, and that's how we'll find the points on the curve. Okay, the points on the curve whose tangent lines would be parallel to this line right here. So let's try that out. Okay. Given y equals x minus 1 over x plus 1. Okay. Now that line, okay, has what slope? Well, we could find the slope by, one way is, we could find 2 points on this line and then we can calculate the rise over run. Another way is formulaically, we could transform this from this form into the slope-intercept form of the equation of a line. So we can do that. We'll try that. So negative 2y would equal negative x plus 2, and then we can divide by negative 2. Right? And what's most important to us is what is the value of m? Okay, that would be the coefficient of the linear term here. So we have y equals 1/2 x minus 1. Okay, that's the line that we're looking at right here, and the slope of that line is 1/2. Okay, we want y prime of x to equal 1/2. Right? We want to let y prime of x equal to 1/2 in order to be sure that we would have tangent lines that are parallel to this line here. We need the function y prime of x, right? And that's going to give us an equation we can solve for x. And for all those values of x, we would have specific locations of points on the curve, okay? And then we can write the equations of the tangent lines. So y equals x minus 1 over x plus 1, we need y prime of x. X minus 1 over x plus 1, that's a quotient, okay? So low d high minus high d low, don't forget the square below, all right? So the low function now is x plus 1. The derivative of the higher function, that's the derivative of x minus 1 with respect to the variable x, that would just be 1. Minus the high function, which is x minus 1, times the derivative of the lower function, derivative of x plus 1 with respect to x is also 1. Right? And square the denominator, x plus 1 quantity squared. Here's my notation again, y prime. We just found a formula for y prime as a function of x, right? We have y prime of x. Okay, so now we're going to let y prime of x equal to 1/2 in order to solve for x. So we set 1/2 equal to this. And let's clean this up a bit. X plus 1 minus, distribute this minus, x plus 1, we distribute that, over x plus 1 quantity squared is a rational equation for us to solve. Solve for x. Okay? And let's note, because this is a rational equation, let's note to restrict the domain. Okay, the domain of this is that x is not equal to -1. That's so we can watch out for extraneous solutions, right? It's a rational equation. Okay? Rational equation. We have to watch out for extraneous solutions. We should check our answers. All right, so I'm checking the domain right now. There's one way of checking to see that we don't get an extraneous solution. Let's solve. And we can simplify the numerator here. It looks like these x's are going to cancel each other out, and then 1 plus 1 gives us a 2. So 1/2 equals 2 over x plus 1 quantity squared. I'm going to multiply by the common denominator to both sides, which in this case, the LCD is 2 times x plus 1 squared. Multiply both sides by that. We get the result of cross-multiplying. That's x plus 1 quantity squared is equal to 2 times 2, and 2 times 2 is 4. Expand in order to solve, we don't have to expand actually, right? We have x plus 1 squared is equal to 4. Let's use the square root property. This means x plus 1 is equal to plus or minus 2. All right, so we took plus or minus the square root of 4, which is plus or minus 2. So we have either x plus 1 equals 2, or that x plus 1 equals negative 2. If x plus 1 equals 2, then that means that x equals 1. If x plus 1 equals negative 2, then that means that x equals negative 3. So we have two values of x, that is y prime of 1, okay, and y prime of negative 3. We know that each of those should evaluate to 1/2. That is, the slope of the tangent line to our curve should be 1/2 when the input is 1 or negative 3. And we can check to see if that's correct by going back to our derivative. If our derivative is correct right here, if we plug in either 1 or negative 3, if you plug in a 1 for x, you're going to get 2/4, which is 1/2. If you plug in negative 3, you'll get 2 over negative 2 squared, which is again equal to 2/4, both of which are equal to 1/2. So these seem like reasonable values, and certainly they're not extraneous because they're not equal to the domain restriction here. Okay, so hence we want tangent line equations at the points on the curve, okay, at the points 1 comma y of 1 and negative 3 comma y of negative 3. Those are the 2 points, okay. Each have a slope, okay, of 1/2. Now we need to know what is y of 1, what is y of negative 3. So let's go back to the original function. Y equals x minus 1 over x plus 1, so that we can find the actual point on the curve, right? In order to write the equation of a line, like y minus y1 equals m times x minus x1, to write this equation, we need to know slope and both the coordinates of a point, right, in order to write the equation of that line. So y of 1, first of all, okay, is going to be 1 minus 1 over 1 plus 1. The function was x minus 1 over x plus 1. This gives us 0 over 2. That equals 0. So we have the point 1, 0, okay, and the slope is 1/2, right? So the equation, an equation for that would be y minus 0 equals 1/2 times x minus 1. That would be one way to write that equation. Or another way is to write y equals 1/2 x minus 1/2. Another way to write that equation of that tangent line. Now y of negative 3. Plug negative 3 into the original function to find the y value of the point. Negative 3 minus 1 over negative 3 plus 1 is negative 4 over negative 2. That equals 2. So the point has coordinates negative 3, 2, and the slope is equal to 1/2. So y minus 2 is equal to 1/2 times x minus negative 3, or x plus 3. And that is the equation of the other tangent line then. The other way we could write that, another way we could write it, if we chose slope-intercept form, let's see, it would be y equals 1/2 x, and then we get plus 3/2, and then we're going to add 2, so 2 plus 3/2 is plus 7/2. Okay. So now we have two equations of lines. They are tangent lines to the curve. They are parallel because the slope is 1/2 in each case. They are parallel to this line right here. So those would be the two equations we are looking for. So now let's take a look at another interpretation, a geometric interpretation for our product rule. Okay. So this exercise is actually quite similar, although a different interpretation by factor using the graphs. It's quite similar to an exercise we just did. This one right here, right? In this one, it's the symbolic case where we're given not even the rules of the functions, but we're given outputs and we're given values of the derivative at particular points, and then we're putting them together in combinations in order to find the derivative of some combination of those functions. So same idea, although expressed graphically, geometrically here instead. So we're given the big F of t is the product of little f of t and g of t, okay, for instance, and big G of t is the quotient of the little f of t and g of t. And we're given their graphs here. So the blue piecewise curve is f of t, okay, y equals f of t, and the red piecewise curve is y equals g of t. We'll notice here the domain. Okay. Let's see, the domains for, let's say, let's start with f. Okay, the domain for f, it exists from -5 all the way through to 7, to +7. So f has the domain from -5 to +7. Okay, but what about f prime? What is the domain of the derivative of f? Okay, and in order for the derivative to be defined, we need for the limit in general to exist. It must exist from the left and the right, and they must equal each other. Okay, that's the limit of the slopes of secant lines, not the limit of the function itself. So for example, at a point like this, at 5, -2, the slope from the left and the slope from the right are not the same as each other. So the graph of the derivative of this y equals f of t function, the graph of its derivative would have a jump discontinuity in it, right? It would be, it would be at some negative quantity, and then it would instantly jump up. Okay, it would instantly jump up to some positive quantity. Okay, if we were to graph the derivative of this function there, so we have a discontinuity in the derivative. All right. Also at the endpoints, because we can't take the slopes of the secant lines from the left towards this point and the slopes of secant lines from the right towards this point. So the derivative has a domain on the open intervals from, let's see, from -5 to 5 open, and then from, I didn't write union symbol there, right? Open from 5 to 7, and it's open at 7 as well. Okay, how about the domain of G? Well, G is defined also from -5 to 7, from -5 to 7, and G prime is defined wherever, okay, wherever its derivative would exist. So derivative doesn't exist at corners or at endpoints. Okay, we can define a one-sided derivative, but we're not using that right now. So G prime would exist from, on the open interval, from -5 to -3 open, and then union. -3 to 2 open, union. 2 to 4, so along this segment here, union, and then from 4 to 7. Okay, just to note that as a review at this point, the domain of the function is not necessarily the same as the domain of the derivative in all cases. It depends on, we can use the geometry to try to establish where the derivative might or might not exist as well. Okay, but let's find one derivative of f and one derivative of g for this particular exercise. I'm going to start by finding the derivative, so the big F prime of 0. Okay, so we'll say part A. Find big F prime of 0. Okay, now in order to find it, first I want to find a formula for f prime of t, big F prime of t, by using the fact that big F of t is a product. Okay, so here's our first step. F prime of t, right, we're using this, right? Big F of t is f of t times g of t, a product. So we use the product rule. So this is equal to f of t, g prime of t, plus f prime of t, g of t. Then we can plug in 0. So big F prime of 0 is equal to f of 0, g prime of 0, plus f prime of 0, g of 0. And we need to find those 4 bits of information by using the graph. So let's start by finding f of 0 and f prime of 0. Okay, what is f of 0 equal to? What is f prime of 0 equal to? Let's go to the graph. Now f is the blue curve. Okay. It's the blue curve, and so when we are talking about f of 0, we're talking about this point right here, and we're talking about the slope of the curve, which is the same as the slope of this line, this a line segment here. We want to know that slope, and we want to know the y value right there. And we don't want to guess those values. We want to know what they are precisely if we want to get this correct. So we need to find information about that location right there. How can we find it? In this case, we can find it by figuring out what is the equation of this line. We have a line that goes from a line segment that goes through the points -5, 3, and 5, -2. Okay, that's the one that goes through where the input is 0. Okay, the equation of the line that goes through the points -5, 3, and 5, -2. Okay, find that equation. Let's find the slope of that line. Okay, so -2 minus 3, y2 minus y1 over x2 minus x1. And that gives us -5 over 10, which is -1/2. And now we can write an equation of the line by choosing any one of these 2 points along with the associated slope. So how about y minus 3 equals -1/2 times x plus 5. That would be an equation of that line right there. Okay, so if I call this L1, for instance, okay, L1, okay, this line right here, okay, this line right here is L1. Okay, so I'll call it L1. All right, we have the equation of that line. Now, y is another name for f of x, right? So this is the same as saying f of t in this case, right? F of t is equal to, let's say, -1/2 t. All right, use t here. -1/2 t, and then this would be what? -5/2, and then add 3, and 3 is equal to 6/2. So 6/2 minus 5/2 is 1/2. So this should be a plus 1/2. Okay, so using the equation of the line, we found f of 0, plug in 0, we get 1/2. So f of 0 is equal to 1/2. And f prime of 0, well, the derivative of this with respect to t is just -1/2 for any value of t. All right, it's constant rate of change. So -1/2. Right, for f prime of 0. So we have 2 of these 4 pieces now at 0 figured out. Okay, we also have a general function for f of t, okay, which we can use in further exercise as well, as long as we are on this segment between -5 and +5. If we were asked to find out what is big F prime of, let's say, 6, then we would have to instead figure out the equation of this line, okay, in order to find out what is f of 6 equal to and what is, f prime of 6 equal to. We would really want to have the equation of this line because the graph is not necessarily precise enough for us to just estimate it. Okay, we should really, we really do need the equation for it on that piece. All right, well, so we also need, of course, g of 0 and g prime of 0. Okay, so how can we find that? Well, choose a different color here. Purple. There we go. All right, so g of 0 would be this point right here, and g prime of 0 would be the slope of this line right here. Okay, and so that is the line that connects the point, or goes through at least the point, -3, 4, and 2, 2. All right, I'll call that L2 right there. Okay, that's our line 2. -3, 4 to 2, 2. Okay, let's find that. Equation of the line through -3, 4, and 2, 2. Okay? So, repeat the process. The slope is y2 minus y1 over x2 minus x1. Okay, in this case, that gives us what? -2 over 5. Okay, and so we can write an equation aligned with through this point with this slope. Y minus 4 equals negative 2/5 times t plus 3. You know, you could have used the coordinates from the other point as well. That would have been totally fine. In fact, maybe even easier than these numbers I chose. Usually smaller numbers are easier to use than larger numbers. But here we are. I'm going to write this then as the function, let's see, g of t. In fact, like up here when I said this was f of t, this isn't completely f of t, right? This is only f of t on one particular piece. That was only f of t between -5 and +5, right? That was a piecewise function. So on -5 is less than or equal to t is less than or equal to 5, okay, we have f of t is defined this way because it was piecewise. Now, for g of t, we're defining it along this segment. That's between -3 and +2. So on -3 is less than or equal to t is less than or equal to 2, we have g of t defined how? Well, g of t is equal to -2/5 t, and then we're going to get -6/5, and then add 4. 4 is equal to 20/5, so 20/5 minus 6/5 is plus 14 over 5, 14/5. So there's our g of t on that segment of the domain, right, that goes through where t is equal to 0, which is what we want. So what is g of 0? By use of our equation here, g of 0 would be 14/5. And what is g prime of 0? The derivative of this with respect to t is the slope of the line, -2/5. 14/5 and -2/5. 14/5 and -2/5. Okay? So now, f prime of t, okay, f prime of 0 was this formula right here. Okay, now we can plug in the 4 quantities we found and determine what is f prime of 0 finally. F prime, all right, so repeating this, right? F prime of 0, okay, is f of 0 times g prime of 0 plus f prime of 0 times g of 0, okay, is equal to, let's see, f of 0 was equal to 1/2. Okay, g prime of 0 is -2/5, and then plus, now f prime of 0 is -1/2, and g of 0 is 14 over 5. So this is -1/5 minus 7/5, and that equals -8/5. So there's big F prime of 0. Okay. Now let's repeat the process by doing one for G, but let's take a different input value. How about G prime of -2? Let's find G prime of -2, where G of t is the quotient F of t over little g of t. Right? So B. Find big G prime of -2. Okay? And that's where g of t, big G of t, is little f of t over little g of t. So we need quotient rule. Low d high minus high d low. Don't forget the square below. Okay, and let's find big G prime of t. So that would be low d high minus high d low over low low. Right? And so therefore big G prime of -2, okay, is G of -2 F prime of -2 minus F of -2 G prime of -2 over G of -2 quantity squared. We need to evaluate F and G, F prime and G prime. We still need 4 components here, right? But at a different input value than we did previously. F of -2 f prime of negative 2, g of negative 2, and g prime of negative 2. But fortunately for the value that I've chosen, negative 2, okay, t is negative 2 is contained within the same subsets of the domain. So we can still use these pieces, right? If t is negative 2, we are between negative 5 and 5, so f of negative 2 would be evaluated by this function right here. And again, t is negative 2, that's confined within this domain, so we can use this rule right here, okay, for g. Okay, so still using that f of t is negative 1/2 t plus 1/2, right, because t is equal to negative 2, okay, and negative 2 is between negative 5 and positive 5. And then still using that g of t is negative 2/5 t plus 14 over 5, because t is equal to negative 2, that is between negative 3 and positive 2. Okay, so we can still use these two rules. So using the f of t, we can find out what is f of negative 2. Plugging it in, negative 1/2 times negative 2 is positive 1, so we get 1 plus 1/2, and that equals 3/2. Okay, and then what is f prime of negative 2? Well, it's the derivative of which is equal to negative 1/2, because this is a line, that derivative is constant, so negative 1/2 for f prime. And g of t, use that to find g of negative 2. G of negative 2, we're going to get positive 4/5 plus 14/5. That gives us 18/5. And then g prime of negative 2, okay, is negative 2/5. Is the slope of that line. All right, negative 2/5. And g of negative 2 was 18/5. Okay, so now plugging into our formula here by virtue of the quotient rule, okay, plug in all of our values. G prime of negative 2 is equal to, let's see, g of negative 2 first, well that's 18/5. F prime of negative 2, well that's negative 1/2, minus f of negative 2, which is 3/2, times g prime of negative 2, which is negative 2/5. And then the denominator is that g of negative 2 quantity squared. So that is 18/5 quantity squared. Now let's simplify this. So this is going to be, let's see, cancel 18 with 2, we get a negative 9 over 5, and then minus minus turns to a plus. This is, the 2's are going to cancel each other out, so plus 3 over 5, and then the denominator, we have, let's see, an 18 squared and 5 squared. So now we can multiply the top and the bottom each by 5. So the numerator would just leave us with negative 9 plus 3, which is negative 6, because we get to cancel out these 5's. And the denominator, we have 18 squared, okay, over 5, because we get to cancel one of these 5's down here. Now I can move this 5 up to the numerator, so we have negative 6 times 5 in the numerator, and we have 18 times 18 for the denominator. We can cancel a 6 with an 18 to get a 3, so we're left with negative 5 over 3 times 18, which is 54. So negative 5 over 54, that would be big G prime of negative 2 by use of the quotient rule and the geometry of these piecewise functions. Okay, let's move ahead, take a look at a word problem example. Drug concentration. The concentration of a drug in a patient's blood T hours after injection is given by the function f of t equals 0.4 t over 2t squared plus 1 in milligrams per liter. Find the rate of change of the concentration with respect to time. Okay. That is, we want to find f prime of t, or in Leibniz notation, df dt. The function that tells us the derivative. Okay, would presume, if we're saying that this is t hours after injection, then we would presume that the domain is that t is greater or equal to 0, because this is after the injection is given. Okay, so time would not be less than 0. What is the concentration of the drug in the bloodstream at time 0? At the instant that it is given, what concentration do we get? Plug in 0 to find out. 0 divided by 1, which is 0. All right, so it starts at, the concentration was 0. But if we wanted to know after a certain amount of hours have gone by, like after 1 hour, what is the concentration? You could plug 1 into the function to find the concentration in milligrams per liter. Now, we're not asked to find that. What is the concentration? That would be an algebra question. We're asked to find the answer to a calculus question. How fast is that concentration changing with respect to time? Okay? And we're going to find that rate of change at different quantities of time. 10 minutes, 30 minutes, 1 hour. Note that t itself is in hours. So if we're talking about 10 minutes, what value of t would we choose? So if you take 10 minutes multiplied by 1 hour for every 60 minutes of time, a unit ratio, we could cancel minutes with minutes. We get 10 over 60, which reduces to 1/6 of an hour. So we would be evaluating not the function at 1/6. We're looking at rate of change. We want to evaluate the derivative at 1/6 in order to answer the question, what is the rate of change? How fast is the concentration changing after 10 minutes after the injection is given? And then what about after 30 minutes? After 30 minutes, t is going to equal 1/2. And after 1 hour, t is going to equal 1. All right, so if I could say in general for part B, we are finding like an f prime of a for different values. In part C, interpret the answer. Instantaneous rates of change. Okay. So for A, we are finding f prime of t, which is the time rate of change, the derivative with respect to time of the function 0.4t over 2t squared plus 1. So we need the derivative with respect to t of a quotient, so we need the quotient rule. So low d high minus high d low over low low. Okay, so the lower function is 2t squared plus 1. The derivative of the high function is 0.4 minus the high function is 0.4t times the derivative of the lower function. So what's the derivative of 2t squared plus 1? Derivative of 2t squared plus 1. Okay, that is 2 times the derivative of t squared, which is 2t, plus the derivative of 1. Derivative of 1 is 0. So the derivative of 2t squared plus 1 is 4t. So 4t. And then over the denominator squared. And so here is our f prime of t function. And this is fine for an answer for part A. And it shows how we found the answer by use of the quotient rule. Now, in order to move into part B, where we're going to start plugging in values of t, we might want to either leave this alone and just plug values of t into this the way that it is, or we might want to clean this up. Okay, it's up to the observer. I'm going to go ahead and clean this up. I would prefer to do that. So I'm going to see, how can I factor the numerator? I can factor out 0.4 from both of these. So take out the 0.4. That leaves us with 2t squared plus 1 from the first term. And then minus, we're left with a t times 4t, so 4t squared. The denominator is still 2t squared plus 1 squared. Numerator, we can clean up a little bit further. Let's see. 2t squared minus 4t squared is minus 2t squared. So I'll write this as 1 minus 2t squared. And the denominator is still 2t squared plus 1 quantity squared. So I'm going to use that expression right there in order to evaluate the rates of change. Starting with the rate of change of the concentration after 10 minutes. And after 10 minutes, again, that would be after 1/6 of an hour. So we are evaluating first f prime of 1/6. So we plug 1/6 into our derivative for our time value. So 0.4 times 1 minus 2 times 1/6 squared, which is 1 over 36. Okay. Right, I'm going to leave that as a fraction, by the way, because that is exact. If we turn this into a decimal now, we have to be very careful, because then later on, if we turn this into a decimal, we have to use an approximation for that decimal. So I'm going to leave this written as a fraction here, so it's more precise. I'll use a decimal later at the end in order to approximate the answer. But in order to avoid accuracy error, I don't want to turn this into a decimal right now. That is, I don't want to round this to some decimal quantity right now, because then we're going to be applying it in further operations. And when you round early in a process, it leads to error later in the process. So if you're going to round it as a decimal now, you'd want to take it out to several decimal places beyond where you want your answer in the end to be. Okay, in the end, let's say we round, okay, I'm going to round to, let's say, 3 decimal places in the end. Okay, but not until the end of the process. I don't want to do any rounding right now to preserve the accuracy in our answer. Okay, now the denominator would be, let's see, 2 times t squared, so 2 times 1 over 36 plus 1 quantity squared. So if you plug all this into your calculator real carefully, you can get an approximation. Okay, I'll try to simplify it a bit here. 0.4 is what, 2/5, and then this is 1 minus 1 over 18. This is 1 over 18 plus 1 quantity squared. All right, so what's that? 2/5 times 17 over 18. This is 19 over 18 quantity squared. Right, so I get to cancel an 18 here with one of the 18s down there. Let's see, not much else cancels, right? So you get 34 over 5. And the denominator looks like a 19 squared over 18. So 34 times 18 over 5 times 19 squared. I'm going to go to the calculator with that expression. Okay, get an approximation. 34 times 18, divide that by the quantity. I'm using a parenthesis here. 5 times 19 squared. Okay, and I'm getting that this is approximately 0.339. The units of measurement here, well, F, the original function, was milligrams per liter, but now we have taken the derivative with respect to time. That is, we want the rate of change of this concentration per unit time, where the unit of time is hours. So this, the derivative of F, is milligrams per liter per hour. Okay, all right, milligrams per liter per hour is what we're looking at here. That'll help us with our interpretation, like we're asked to do in Part C. So what you should try right now is determine what is the rate of change of the concentration after 30 minutes. That is, evaluate the derivative at an appropriate value of the input so that you can find the rate of change of the concentration after 30 minutes. Okay? Rate of change after 30 minutes. Okay? You try that out right now. So, in order to find that rate of change after 30 minutes, you should be evaluating f prime at 1/2 or at 0.5 if you'd like to use a decimal, because you can use an exact decimal for 1/2. So you want to find out what f prime of 1/2 is. Okay, so that's going to be 0.4. All right, using my simplified function right here. 1 minus 2 times 1/2 squared, so 1 minus 2 times 1/4, okay, over, let's see, 2 times 1/2 squared, so 2 times 1/4 plus 1, that quantity squared. Okay, so 0.4 is the same as 2/5. I'm going to write it as 2/5. This is 1 minus 1/2, which is 1/2. Down here we have 1/2 plus 1, which is 3/2, so 3/2 quantity squared. Okay, so we get to cancel the 2's here. We have a 1/5 in the numerator, and in the denominator, looks like we're going to have 9 over 4. So let's see, this is the same as 4 over 45. Okay, and 4 over 45 as a decimal. Round it to 3 decimal places is 0.088. It just keeps repeating with 8s. So round it to 3 decimal places is 0.89. And the units are milligrams per liter per hour. Okay. And then finally, for part B, what is f prime of 1? That's after 1 hour. F prime of 1, 0.4 times 1 minus 2 times 1 squared over 2 times 1 squared plus 1 quantity squared. Okay, so what's that? 0.4 times 1 minus 2 is negative 1. And then we have 2 plus 1 is 3. 3 squared is 9. So we have 2/5 negative, okay, negative 2/5 divided by 9. So negative 2 over 45. Okay, so 2 over 45 made negative. We have approximately negative 0.044. The next digit is a 4. It keeps repeating with those 4s like that. And that is milligrams per liter per hour. Okay. Let's move to part C, where we need to interpret our results. Okay, so in general, f prime of t is the instantaneous rate of change of the concentration, okay, of the drug in the bloodstream per hour. So for example, f prime of 1/6, right, which was approximately 0.339 milligrams per liter per hour. Okay. The interpretation is 10 minutes after injection. Okay, the concentration of drug in the bloodstream is increasing. Why is it increasing? Because f prime is greater than 0 is why it's increasing. It's interpreted as a slope. So this is increasing, okay, at a rate of 0.339 milligrams per liter, okay, per hour. That is to say, if we were to use this rate of change, if we were to assume that it was going to stay the same for the next hour, we could assume that an hour from now, there's going to be an additional 0.339 milligrams per liter in the bloodstream, per liter of blood, okay, that we would expect in the bloodstream versus what we have right now. Now, notice this derivative does not tell us how much of the drug is actually in the bloodstream. It's the function, the original function, f of t, tells us how much of the drug is actually in the bloodstream. F prime is telling us how fast it is changing, but at that instant. And this is not going to be a constant rate of change. In fact, we can see, if we look at 30 minutes, for instance, we can see that we have a different rate of change, okay, 0.089 milligrams per liter per hour. So that's 30 minutes after injection. What's the concentration doing now? Okay, the concentration of drug in the bloodstream is still positive, right? It's still increasing. Okay, it's increasing now at 0.089 milligrams per liter per hour. Is it going faster? Is it increasing at a faster rate or a slower rate than previously? It was increasing at 339 per thousand, 339 milligrams per thousand liters. Now it's 89 milligrams per thousand liters. So it is a slower rate. Okay? It is a slower rate of increase. If we were to look at a graph to try to model this, we have at time is equal to 0, okay, versus concentration, okay, milligrams per liter, and time is in hours. We might see something where, like, initially there was no concentration of drug in the bloodstream, but it started to increase, but then the rate at which it was increasing was slowing down, right? That is, the slopes of the tangent lines are becoming less extreme, right? They're not as steep as this increases. That's what we're seeing is happening here. The rate of increase is slowing down. Now, what happens at 1 hour? F prime of 1 was approximately negative 0.044 milligrams per liter per hour. That means 1 hour, 60 minutes, right? 1 hour after injection. What is the concentration doing now? The concentration of drug in the bloodstream, okay, is now decreasing, right? Because we have a negative value now for the rate of change. So it is starting to decrease, okay, at a rate of, and since I'm saying decreasing, that includes that we've already interpreted the negative with the word decreasing. It is decreasing at 0.044 milligrams per liter per hour. So back to the graph. That means in the graph, at some point after 30 minutes, but before 60 minutes, at some point between 30 and 60 minutes, it started decreasing. There must have been a maximum concentration in the bloodstream between 30 minutes and 60 minutes. Somewhere between those two, there must have been a maximum concentration. And in fact, as this goes off to infinity, we can also see by looking at the function a little more closely, as t approaches infinity, what happens? As t approaches infinity, we get infinity over infinity. But the denominator has a higher power than the numerator. As t approaches infinity, the concentration is expected to approach 0. So that's as time continues out, we expect this concentration is going to asymptotically approach 0. So the graph is going to look something like this. That is, at 1/6 we see that it is increasing. And then, right, at 1/6 of an hour we see that it is increasing rather steeply, maybe relative to other locations. At 1/2 of an hour, it is still increasing, but not as fast as it was after 10 minutes in. It's still increasing, but by the time we get to 1 hour, it is now decreasing. And asymptotically, we say as time goes off to infinity, we know this is going to approach a concentration of 0 eventually in the future as well. Okay? That is our dynamic interpretation of the concentration of drug in the bloodstream by using the derivative as an instantaneous rate of change of this function. We're looking at the concentration of milligrams per liter per hour, okay, instantaneously. All right, I think there's just one more thing I want to look at. Is just take a look at the higher derivative with the product or the quotient rules. Okay, so let's take a function. Let's find y prime, y double prime, y triple prime. Okay, let's do an example maybe that's not too rough here. All right. Let's take y is equal to, let's see, x squared plus 2x plus 1 times e to the x. Now that's not too bad. Okay. Find the first, second, and third derivatives. Okay. First, y prime. Okay. This will be the only example we'll do. Okay. Y prime is equal to, well, first we can leave the first function alone, and then take the derivative of the second function, right? So let's take e to the x prime, and that gives us e to the x. Plus, now let's take the derivative of the first function, which is 2x plus 2, times the second function left unchanged. Okay, so, right, so this is x squared plus 2x plus 1 prime, right? There's our product rule right there. And let's clean this up so that we get ready to do the product rule again. This is e to the x times, let's see, x squared plus 2x plus 1 plus 2x plus 2. So this is x squared plus 4x plus 3. So there's our y prime. See if you can follow the algebra there for how I've simplified it. Getting us set for finding y double prime, the second derivative. So the second derivative now, let's leave the first one, e to the x alone. Derivative of x squared plus 4x plus 3 is 2x plus 4. Plus, now let's take the derivative of e to the x, which is e to the x. Okay, so that's e to the x prime right there. Okay, e to the x prime, I did right there. And then times the other function left alone, x squared plus 4x plus 3. Now let's simplify this. Factor out e to the x, and then combine these. We have in standard form, there's an x squared, there's a 4x and 2x, which gives us plus 6x, and then 3 and 4 gives us 7. So there's y double prime simplified. Okay. Right, and so we have the derivative of that, right there. All right. Third derivative. Same thing again. Leave e to the x alone, then multiply by the derivative of this polynomial. That would be 2x plus 6. Plus, now we want the derivative of e to the x, which is e to the x. Okay, so e to the x prime is e to the x. And then leave the polynomial piece alone, x squared plus 6x plus 7. And let's just clean this up. Okay, to get a nice clean answer. E to the x times x squared plus 8x plus 7 and 6 gives us 13. Okay. There we go. We have 3 derivatives. Okay, so we can certainly take higher derivatives by use of the product rule. It might be advantageous to us at each step, if we're going to take higher derivatives, it might be advantageous to simplify algebraically what we have. It depends on the actual function itself. What's more time consuming, so to choose between when you apply algebra and when you apply calculus in the process, given that both are most likely required throughout the process at some points, choosing when to apply algebra and when to apply calculus, okay, is an intuition that we should be building. So practice as you're doing the homework exercises, practice maybe different approaches, trying some algebra first and then calculus, or trying some calculus first and then doing the algebra, for example. Continuing to get that practice to sort of get an idea for when it might be easier to apply algebra first, when it might be easier to apply calculus first, for example. And read the instructions to the problems as well. If you're only being asked to find a derivative, if that's it, if that's all I'm asking you to do is to find the derivative of a function and you're done, then I'm really looking for the step where you actually do the differentiation. And that would be like, for instance, this step right here would be where you do the differentiation. And I can read through your work that you did the product rule and you found the individual derivatives correctly and you set up your product rule right. I wouldn't be looking for your simplification of it. Not unless you were supposed to then do something else, like we did in the application problems thus far, where simplification helped, or like here where you then had to find a second derivative where it might be advantageous to you, okay, to simplify it first, okay. But if I don't ask you to specifically simplify on these exercises, then you're not being expected to simplify, and that is meant to be both a time saver for you when taking a test and a time saver for me when I'm grading it, because I'm not looking for ultimately all the algebra you did. I'm looking for the calculus that you've applied. Okay, so try out the homework. Let me know if you have any questions on this content here. All right, and I'll talk with you soon. Take care.